Well, we're going to get started. First, a couple of things before we get into our lesson today, which will be starting chapter 11 today. Most of you here are seniors. That means you have right about 4 weeks of classes left, right? Give or take a day or two. All right. One of the things I wanted to quickly talk about today is making sure that you're in a good spot in my class and your other classes. Your number one priority right now should be to make sure that you're on track to at least graduate, and then whatever else you have going on. You know, if this year has not been particularly kind to you in your academics, you've got to really make sure you're in a position to at least graduate. You know, for my class, if there's classes such as like an English class or a government and economics class, for instance, that you are not passing, those are required classes for graduation. You cannot graduate if you do not pass those classes, right? You need 4 years of English, passing English, right, to get your high school diploma. So if you're not in a position where you're passing those classes, you need to be talking to your counselors, you need to be talking to those teachers, figuring out what you need to do. That should be a number one priority if it has not already happened. For my class, if you're not passing right now, the best thing you can do is just go and try the multiple choice assessments. Right? Even if all you do is the multiple choice assessments and you get like better than like a 2.5 on all of those, you'll pass the course. Right? Even if you don't get to all the other free response question assessments and things like that, if you just do the multiple choice assessments, you'll be in an okay spot. All right. So try to be strategic at this point. Make sure you're in a good spot. If you need help with any of that, I'm happy to meet with you to help discuss those things, look at your grades, try to come up with a game plan if that's something you need support with. Otherwise, you should be talking to your counselor or other teachers that teach those courses you're not doing well in if you have some of those things. It's something I would talk to with all of my AP Stats classes just because this year's been wacky. I want to put some perspective on things. All right. So if you do have any other questions, comments, or concerns about that side of things, please let me know. I'm happy to help. I'm happy to discuss those things. All right. That being said, those of you who are planning on taking the AP exam, you really, 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 really need to make sure that that testing app works on your computer. Some of you have not done that yet. Some of you have done that. If you have a school-issued device, some of them are too old to run the app. If you have a school-issued device that doesn't have the app on it and you try to download it and it doesn't allow it to download, you need to get a different computer. Right? Do not wait until the week of your AP exams to try and get that sorted out. It might not happen in time for you. So you need to check that now. All right. So please do that. Please, please, please make sure you're prepared with the proper computer. The app is working. You can run the app. You can log in, all those things now rather than, when you're supposed to be doing your setup for an exam. That's going to suck. All right. So if you need help with that, you need to let me know so I can help get you in touch with the right people and we can make that happen for you. All right. So any questions, comments, concerns? Well then, we're going to get started with our lesson today. It will be the beginning of chapter 11, If you have something you're taking notes on, you should have that ready. And we're going to get started here. Share my screen. Good morning, Nathan. Come on. Works. All right, so here we go. We are in chapter 11, inference for distributions of categorical data. All right, so now instead of doing just inference about a particular population parameter, like a population proportion or population mean, we're now going to look at entire distributions, right, of categorical data, and not just one part of the distribution. All right. Section 11.1 is our chi-square test for goodness of fit. All right, and yeah, so this is what we're going to do. So after this section, you should be able to state appropriate hypotheses and compute expected accounts for a chi-square test for goodness of fit, calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test for goodness of fit, perform a chi-square test for goodness of fit, which is putting everything in the first two check marks together. And lastly, there's this follow-up analysis. We'll actually talk about that tomorrow. For some reason, they included as the objectives in this set of slides, but they don't actually talk about it. So I have something set up for tomorrow to talk about that. All right, so sometimes we want to examine the distribution of a single categorical variable in a population. The chi-square goodness of fit test allows us to determine whether a hypothesized distribution seems valid. So our goodness of fit is testing whether or not the proposed fit of the distribution, like how much of each things in that categorical variable could be, our category could be colors, right? Red, blue, green, yellow, orange, whatever. And the distribution of those colors is correct or not. That's what this goodness of fit tests for. And we could have categories of eye color. We could have, our categorical data, remember, is things that doesn't make sense to make an average of because they're not necessarily numbers, they're categories. Right. We can decide whether the distribution of categorical variable differs for two or more populations or treatments using a chi-square test for homogeneity. That will be in section 11.2. That is a slightly different test. Oftentimes when we're doing this comparison, we will often organize our data in a two-way table. The chi-square goodness of fit is typically used with a one-way table. We're looking at one set of a distribution. It is also possible to use the information in a two-way table to study the relationship between two categorical variables. The chi-square test for independence allows us to determine if there is convincing evidence of an association between the variables in the population at large. Right, so remember, if there's an association, that means that knowing that one thing happens tells us something about another value or another thing, right? If we get evidence that those things are independent, that means that knowing about one thing doesn't have any effect on the other thing. So that's what that last test can do. And again, that test will come up in section 11.2. So we have three different tests that we can run with this chi-square statistic that we will be exploring in this chapter. See, we need a moment to write anything down so far. All right. So here's an example. Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each of the browns and reds, 14% yellows, 16% greens, and 20% oranges, and 20% blues, 24% blues, sorry. The one-way table below summarizes the data from a sample bag of M&M's milk chocolate candies. In general, one-way tables display the distribution of a categorical variable for the individuals in a sample. Right. So the individuals is the M&Ms, our categories are colors, and this is the count in our bag of 60 M&Ms for each color. Right. The sample proportion of blue M&Ms in this 60 sample is p hat equaling 9 over 60 is 0.15. Right, this is not 24%. So that gives us something to think about here. Now our table's up here. Since the company claims that 24% of all M&M's milk chocolate candies are blue, we might believe that something fishy is going on. We could use the one sample z-test for a population to test the hypotheses, the null hypothesis that p equals 0.24 and the alternative that p does not equal 0.24. This is what we did in chapter 9. Right, where p is the true population proportion of blue M&Ms. We could then perform additional significance tests for each of the remaining colors. So remember, the thing we're interested in is whether or not the entire distribution is correct, not just if one of the colors proportion is correct. So to get that answer, if we're using a one sample z-test, we would have to do that 6 times, once for each color. Performing a one sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons. Right? We'll get multiple different types of results. We might find significance for the color blue, but not for orange and not for green, but then we would again for yellow, maybe again for red and not for brown. So half of them show significance and half of them don't. How do we make a conclusion out of that? We've compared a lot of different things and got mixed bag of results. Does that ultimately mean that the distribution that they've claimed is incorrect? Do we have evidence for that, or do we have evidence that it is correct? Right? We're trying to figure this out. This leads to too many variables, so to say. The chi-square statistic is what we will use here. Performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does, taking all the colors into consideration at one time. For that, we need a new kind of significance test called a chi-square goodness of fit test. Right, we're testing how well our observed distribution fits into the proposed or claimed distribution, hence goodness of fit. The null hypothesis in a chi-square goodness of fit test should state a claim about the distribution of a single categorical variable in the population of interest. Notice that we're writing this just as a statement. We're not giving each parameter and saying that each of those things are this proportion and that might be correct. We're just going to say the company's stated color distribution for M&M's milk chocolate candies is correct. We don't need to provide anything else in that hypothesis. The alternative hypothesis in a chi-square goodness of fit test is that the categorical variable does not have the specified distribution. And so for the alternative, we just copy the entire null hypothesis and then change is correct to is not correct. That's the only thing we have to change. So again, the alternative would be the company's stated color distribution for M&M's milk chocolate candies is not correct. Does anyone need a moment to write anything down? All right, we can also write the hypotheses in symbols as H naught, such that P blue equals 0.24, P orange is 0.2, P green is 0.16, P yellow is 0.14, P red 0.13, P brown 0.13. And the alternative, at least one of the P sub i's is incorrect. And the I here is just a placeholder for whatever color it is. We're saying one of them is not correct, where P sub color equals the true population proportion of M&M's milk chocolate candies of that color. Right, so we can write it this way if we like. In my opinion, that there's more things to go wrong when writing it this way. Right? or that could go wrong. The idea of the chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if the null hypothesis is true. The more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. Right. Again, notice that we are comparing counts. We are not comparing proportions. Assuming that the color distribution stated by Mars Inc. is true, 24% of all M&Ms, milk chocolate candies produced are blue. For random samples of 60 candies, the average number of blue M&Ms should be 0.24 times 60 equaling 14.4. This is our expected count of blue M&Ms. Notice the fact that this is a decimal is not concerning. It's totally fine for our average number of things made to be a decimal, even though, you know, candies are produced in whole pieces. Right. Using the same method, we can find the expected counts for the other color categories. Right, so for orange, 0.2 times 60, 12, green, 0.16 times 60. Right, so we're multiplying the probability or the proportion, the proposed proportion for each color times the sample size to get the expected number of candies for that sample size. Right, so we get all these values. We can then put this into like kind of a side-by-side table here to see the observed versus expected counts. Right, so we're kind of organizing these things along the way. To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming the null hypothesis is true. If the observed counts are far from the expected counts, that's the evidence we are seeking. So we can see it in this side-by-side bar graph. We're comparing our observed versus expected in each category. And we see some fairly large differences between the observed and expected counts in several categories, right? Yellow seems a bit off, blue seems a bit off, orange. The other ones are off, but not terribly far. Right? How likely is it that differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars Inc. All right, which means when we're asking this question, how likely is it that differences this large or larger would occur, that's p-value. All right, so we're going to be finding our p-value, but we need something else first. To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is the chi-square statistic. So we have a new little statistic. We've got a few other test statistics, right? Our Z statistic and our T statistic that we use when performing significance tests. Now we have a third one. And this is the formula. The chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi squared, that's the Greek letter chi squared, equals the sum of the observed minus expected squared divided by expected, where the sum is over all possible values of the categorical variable. Right, so for our example, we have 6 colors. We'll be adding up 6 of these, where the observed and expected is the observed and expected of that color. Right. This is very similar to variance when we're dealing with like, quantitative data. Right? The variance tells us, you know, on average, how far away things are. What's the spread of everything? Right? This is kind of similar to that. Not exactly the same, but similar. So we need a moment to write this down. So here's our table again. The table shows the observed and expected counts for our sample of 60 M&Ms milk chocolate candies. We need to calculate the chi-square statistic, which is here. All right. So we've got each of our colors represented by these 6 fractions, right, that we're adding up. Where we have observed minus expected squared divided by expected for each color. All right. We sum all these things up, right? And we ultimately get 10.180. So this is our chi-squared statistic. Think of chi-squared as a measure of the distance of the observed counts from the expected counts. Large values of chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far from what we would expect if the null hypothesis were true. Small values of chi-square suggest that the data are consistent with the null hypothesis. All right, essentially, when things are more spread out, that's evidence against the null hypothesis. When things are less spread out, smaller number for the statistic, that's evidence saying that our null hypothesis might be true. All right. We computed the chi-square statistic for our sample of 60 M&Ms to be chi-square equaling 10.180. Because all of the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution with degrees of freedom 6 minus 1 equaling 5. Wait, I skipped a slide. Sorry. The sampling distribution in chi-square statistic is not a normal distribution. It is a right-skewed distribution that allows only positive values because chi-square can never be negative. When the expected counts are all at least 5, the sampling distribution, right, notice we have a condition here. We'll get to that again later. Sampling distribution of the chi-square statistic is close to a chi-square distribution with degrees of freedom, df, equal to the number of categories minus 1. So in this case, different from when we're dealing with population means and estimating population means, degrees of freedom is based on the number of categories. It is not based on the sample size. Remember when we're determining degrees of freedom for estimating means, that's always based on our sample size minus 1. This is now categories minus 1. Right. So now back to this one. We've got our chi-square statistic, it's 10.180. And our degrees of freedom are 5 because we had 6 categories, the 6 different colors minus 1, and that is 5. So it will use this distribution with degrees of freedom 5. Our chi-square statistic is 10.180. It lands about here. So the shaded area above that is our p-value, the proportion under the curve, that large or larger. To find the p-value, we use table C. It's the only table in our formulas and tables packet or link that we haven't used yet. And look at the degree of freedom equaling 5 row. So they have a little excerpt of that here. We have our degrees of freedom 5. In this row, 10.180 falls between 9.24 and 11.07. And we follow that back up to our p-value, right? And that means our p-value should be between 0.05 and 0.1. So this table C works very similar to table B when using a test statistic to find a p-value. Since our p-value is between 0.05 and 0.1, it is greater than alpha equaling 0.05. Therefore, we failed to reject the null hypothesis. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. Okay. So this is our conclusion, essentially, right? P-value is greater than 5, so we failed to reject the null hypothesis. We do not have evidence, we do not have sufficient evidence to conclude that their claim is not correct. Is there anything I can clarify on this example? So now we've seen all the bits and pieces. We're going to put this all together into how to actually carry out a test, right? We must check conditions, right? And our conditions for performing a chi-square test for goodness of fit are the random condition, which is the same as the random condition we've seen for every other test and confidence interval, all that stuff that we've seen previously. Right? It needs to be random. The data come from a well-designed random sample or from a randomized experiment. We need to check the 10% conditioning when sampling without replacement. All right, our large counts condition, while it uses the same name as we've seen previously, is a little different. This is saying that all expected counts are greater than 5. Right? They have to be at least 5. This is different than the large counts that we've seen for proportions. That one is saying we have at least 10 successes and failures in our sample. This is now saying, hey, each of our expected counts must be 5 or more. Before we start using the chi-square goodness of fit test, we have 2 important cautions. 1, the chi-square test statistic compares observed and expected counts. Right? Don't try to perform calculations with the observed and expected proportions in each category. You will get wildly incorrect answers. When checking the large sample size condition, be sure to examine the expected counts, not the observed counts. Right, we're only going to use the expected counts for large counts condition. Does anyone need a moment to write anything down from this screen? Raise your hand. And then we have the rest of the carrying out of the test. Right, suppose the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category, perform a test of the null hypothesis is that the stated distribution of a categorical variable in the population of interest is correct. The alternative is that the stated distribution of the categorical variable in the population of interest is not correct. Start by finding the expected count for each category, assuming the null hypothesis is true. Then calculate the chi-square statistic, chi-squared equaling the sum of the observed minus expected squared divided by expected, where the sum is over the k different categories. K is a variable representing the number of categories. The p-value is the area to the right of chi-square under the density curve of the chi-square distribution with k minus 1 degrees of freedom. So this is like the process, so to say, in a nutshell. Would anyone like a moment to write anything from this screen down? All right, so we'll do an example going through this entire process. All right, here we have our problem. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1 is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on birthdays for the 80 players. Notice we've broken this down into 4 quarters or 4 categories here, breaking the year into 4 quarters. Right. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? Right. So this is the question we're trying to answer. Notice we're starting our 4-step process. This is going to help us keep our work organized and make sure we cover all things we should be doing. So state, we want to perform a test of the null hypothesis. The birthdays of all NHL players are evenly distributed among the 4 quarters of the year, versus the alternative that the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. No significance level was specified, so we'll use alpha equaling 0.05. And again, whenever a significance level is not specified, use the default of 0.05. Plan. If the conditions are met, we will perform a chi-square test for goodness of fit. Random. The data came from a random sample of NHL players. 10%. Because we are sampling without replacement, there must be at least 10 times 80 equals 800 NHL players in the season when the data were collected. There were 879 NHL players. Large counts. If birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times a quarter equals 20. These counts are all at least 5. Right. Now we do the math. We have to calculate our test statistic, which is our chi-square statistic. For each quarter, we have a fraction that we're adding in here, 32 minus 20 squared over 20, 20 minus 20 squared over 20, 16 minus 20 squared over 20, 12 minus 20 squared over 20. We have our observed count and expected count for each quarter. All right. So we have 7.2 plus 0 plus 0.8 plus 3.2, and we get 11.2 as our test statistic. Right. This would use the chi-square distribution for degrees of freedom equaling 3, because we have 4 categories, 4 minus 1, 3. Our chi-square statistic is going to land right over here on our distribution, and the p-value is everything under the curve, right? The proportion under the curve greater than or chi-squared. As the excerpt shows, chi-squared corresponds to a p-value between 0.01 and 0.02. We have degrees of freedom 3. 11.2 is between 9.84 and 11.34, which means the p-value must be between 0.01 and 0.02. Again, notice when we're writing this, we put the smaller value first. When we write it, the table unfortunately goes in the reverse order. Is there anything I can clarify about the calculations done here? Are there any questions?
How did you get degree of freedom number 3?
So again, we have in this example 4 categories for birthday. They can be born January through March, April through June, July through September, October through December. There are 4 categories, and our degree of freedom is determined by the number of categories minus 1. So we end up with 3.
Okay, thank you.
You're welcome. So now we're ready to write our conclusion. Because the p-value 0.011, which they have an exact p-value because they probably put it in the calculator and didn't show that part, is less than alpha equaling 0.05. So we reject the null hypothesis. We found significant results. Right? We have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Right? So there we have it. Is there any questions about our conclusion? Okay. So that brings us to the end of the presentation here. We have our chi-square test for goodness of fit. We went through these first 3 check marks. We will talk about the follow-up analysis tomorrow in our class tomorrow.